Hi, here's another quick demonstration of one of the problems from the Connect homework, Chapter 6. This, I believe, is the second problem out of the assignment. So you've got a reaction going on, 55.1 grams of tin dissolving in acid, and that creates gas. It creates this hydrogen gas right here. And so we have to figure out how much work is done. Again, the key to this chapter is kind of just thinking through all of the formulas and which ones apply when. So work is a very specific thing, and the definition that we're using in this chapter for the most part is work is equal to the pressure times the change in volume of an expanding or contracting gas. And so when gas is formed from reactants that are not gases, work is being done by that system, the reaction on the surroundings. So we're going to have to figure out how much volume of gas is created from this 55.1 grams of tin using stoichiometry. So we're given the balanced chemical equation. Let's go ahead and start using some of our techniques from previous chapters. We know we have 55.1 grams of tin. We are going to have to convert this to moles. That's the first step in any gas or any stoichiometry problem. If we look in our periodic tables, we should see that 1 mole of tin has a molar mass of 118.71 grams. So yeah, 1 mole has that mass, and setting it up like this will allow our grams to cancel out. Before I equal this out though, let's go ahead and convert this from moles of tin to moles of the hydrogen gas. And since there's no coefficient on either of those reactants or products, we know that 1 mole of hydrogen is created from every 1 mole of tin. So this gives us a value of 0.464 moles of tin. Moles of tin, but also moles of hydrogen gas, which is what's more important because it's the gas that's doing the work. And keep in mind this problem doesn't ask anything about heat, so we don't need to worry about it. Now, all we need to do at this point is figure out what volume that molar amount of tin is going to take up, and we do that using the ideal gas equation. Really, this is the most important equation from the gas laws chapter. You know, we studied Boyle's law, Charles's law, etc., but those were always about a specific gas sample with one variable changing. So taking a balloon and putting it in a different temperature water bath, or compressing a syringe. So for this new gas that's generated from reaction, we're going to need to know, we know 3 of the 4 variables, we'll be able to solve for the volume. So rearranging this here, volume equals nRT divided by pressure, and that's going to equal my 0.464 mole that was just created times the ideal gas constant, 0.0821 liters atmospheres per mole Kelvin, times the temperature that was given, which is the 20 degrees Celsius in this case, and it'll need to be converted to Kelvin by adding 273.15. That will be in Kelvin once I do that addition. Whoa, that's a bad line. But divide that by 1 atm. So if I do add all that math, I should get 10.156 liters. And work is simply equal to the pressure times that change in volume. Pressure is 1 atm, or sorry, 1.1 atm, times that change in volume. And this gets us units of atm liters, or liters atmospheres. And those are energy units. As kind of contrary as it might sound, we went over it in class a while ago, but we can use the relationship that 1 liter atmosphere is equal to 101.3 joules, and so that gets us 1,131.6 joules of work done by this reaction. Now, this is work being done by the system on the surroundings, and so we should express that as a negative. And we also have 3 significant figures on most of the givens, so we should express this to 300 to 3 significant figures. So that's minus 1,130 joules.